Oh, I have to give my consent here, right?
Yeah, you have to say yes.
Yeah.
Okay, so welcome to our Applied Mathematics and Complex Systems Group seminar. Today, it is my pleasure to introduce to you Bedartha Goswami. He is currently a junior group leader at the University of Tübingen, but I think we know us for quite a long time now, because Bedartha worked with Jürgen Kurz, got his PhD at the University of Potsdam, if I'm not mistaken, but working at the Potsdam Institute for Climate Impact Research. He was always a friendly face when I was visiting PIC. And in addition, I do think his research is quite relevant to what we are doing. We all hopefully have read the 2009 Nature paper of him and Niklas as the first author. And today he's going to talk about his field, which is transitions in time series applied to paleoclimate questions, but with the additional twist of adding proper uncertainties and doing that most likely in a fully Bayesian framework. Hopefully.
Yeah.
Okay, so to you.
Yeah, thank you, Thomas. And yeah, thanks for having me here. This is work that we did during the end of my PhD, and we basically ended up publishing it a couple of years ago. So I worked a lot on my PhD on paleoclimate data sets, and one of the main things in paleoclimate data is that you have uncertainties on the time scale, which we ended up transferring to the signal, and then you have essentially uncertainties in your data, in your signal. And so this work is essentially geared towards motivating a new sort of representation of time series that inherently, very natively incorporates uncertainties, and to detect abrupt transitions in it is, in my opinion, just a kind of a case study on how to work with this kind of representation. Here's a brief outline of the talk. So what I'm going to do is I'm first going to talk about recurrence networks and how we can use recurrence, what are recurrence networks, and how that essentially helps us reframe the question of identifying abrupt transitions. This is a sort of an independent concept, in my opinion, that can be used separately with or without uncertainties in your time series. The second part would be just talking about this new representation that I mentioned, how we can think of time series as a sequence of probability distributions. Then we basically combine the two ideas and look at a contrived synthetic example in which we put in a few transitions and then try to identify them. And finally, I'll show you a real-world example, which is basically a paleoclimate data set that starts at around 30,000 years from now ago and goes back further into the past, so another 15,000 years. So it goes from 30,000 years to 44,000, 45,000 years in the past. And that's what's basically when we had ice more or less all over the planet. It's the last glacier. And this is data from actually our collaborators, Sebastian Weidenbach's group. And actually this data is from a cave where, not very far from where I grew up in the northeast of India. Okay, so let's get started. First, to talk about recurrence networks and abrupt transitions. Just so that maybe some of you already are familiar with this, but just so that all of us are on the same page, what are recurrence networks? To put it very briefly, in a nutshell, is to think of it. So if you have this trajectory, I hope you can see the most point. So if you have this blue trajectory that in the phase space that goes around has some oscillations and maybe some drift, and then on this blue phase space trajectory, we have the black measurement points. So those are the time points where we have sampled the trajectory, and that of course constitutes our time series. A recurrence network would essentially, you can think of it as a kind of a nearest neighbor network, which stays embedded in your phase space. So we can pick up, let's say, one of these sample points, which is now here in red, and think of some kind of a metric which allows us to, in this, it's very simple, a Euclidean metric, but it can be different kinds of metric like nearest neighbors. So you can think of some kind of metric that allows us to talk about points which are very close to this within a kind of an epsilon neighborhood. And then we put edges between these points that are inside this neighborhood and do so for all points. And then in the end, you can get a kind of an adjacency matrix, which basically depicts the network embedded in your phase space. How do recurrence networks help us detect transitions? For that, here's a simple schematic. Again, a very contrived, simple example. You essentially have to start at the top left and go clockwise to understand this figure. So let me just walk you through this. So in the top left in plot A, what we see is we have a signal, which is this, let's say the true value of the signal is this gray line in the background. And there is obviously, I've put in a sudden jump right at the middle, where it's a kind of a transition between two states. But we've sampled the signal at a slightly coarser resolution shown by this black line here. Now, to construct a recurrence network, what we can do is first we can calculate all pairwise distances, and that is then shown in this distance matrix in the bottom left, where dark reddish colors represent short distances, and yellowish to white colors represent very large distances. It's a very simple one-dimensional distance, Euclidean distance. And now you can threshold essentially this distance matrix according to your a kind of a predefined neighborhood size epsilon, which can then give you a binary adjacency matrix, which is essentially the matrix adjacency of your recurrence network. Now, it's very obvious that a transition between two different states of dynamics is represented as a kind of a block structure in your adjacency matrix. Essentially, what it means is that communities in your recurrence network essentially depict parts of the time series trajectory that were located in a really close-knit space of the phase space. And then if you have moved to a second community, then the time series moves to a kind of a different part of the state space and gets confined there. And then the jump between these two communities, the border of these two communities, essentially your time point of transition. What this means is that identifying transitions in a time series can essentially be reframed as the question of identifying communities in your recurrence network. And that is the concept that we have used to detect abrupt transitions in a time series. Right? So that was the first part. Then the second introductory part would be to think of time series as a sequence of probability distributions. This is again, as I said, it sort of came about because we were already dealing with the situation in paleoclimate data sets. But in the end, we realized that this can be a much more general concept and not just confined to paleoclimate. So I will try to sort of motivate the notion here in a more general way. So you can think of a signal here that I've shown here in this plot here on the right. So you have time going towards the bottom right here, and then you have the signal, value of the signal on this axis here. And you have a gray dashed line, which is, let's say, the true value of the signal. We measure this true signal at these orange sample points, and let's say each of our measurements has some kind of error to it. So our measured points are x of t, and then we essentially have a series of two tuples, x of t and e of t, which is the errors. Now, whether or so in my opinion, irrespective of whether people admit it explicitly or not, most of the time the underlying notion that we have of errors is that it follows some kind of a distribution where most often than not we would intuitively say that the measure where we have the actual x of t, that value is the most likely value, and likelihood of the signal being located at values away from x of t decreases according to the width of your error. So here I've then just schematically shown this as some kind of a bell-shaped distributions. Could be Gaussian, could be other distributions as well. That's not really the point. But the important point here is that erroneous measurements essentially implicitly represent a kind of a distribution around the measured values. And that maybe we can think of now as this distribution rho. I'm using the notation rho, the Greek letter rho, as a notation for probability density. So rho of x given x at x of t as parameters x of t and e of t. So think of it now more generally. So our proposition is that let's just then do away with this whole measured point and the measured error entirely, and just think of the time series as a sequence of these probability distributions, and just sort of throw away, after we've obtained the probability densities for each time point, we don't need the initial measurement set anymore. So what we end up now is that essentially we have a probability of observing the signal at a time t, and then as you change the time measurement sample t, you get different probability distributions. In most cases, it could be that they belong to the same family. It's just that the mean and the variance is being changed, but it could also be that you have more complicated situations. Now, here, one fundamental thing which is very different here is that from the typical time series representations where you have very point-like measurements at different points, is that in the typical representation, you talk about what was the value of the signal at a given time point. In this representation, we rather talk about how likely was it to observe a given value of a signal at a given time, right? So it shifts the focus from knowing the precise value to knowing likelihood of a whole range of values at different times, right? And of course, this is nice and intuitive and elegant, but then it's not easy to work with. Basically my postdoc at PIC was essentially trying to come up redrafting time series analysis in terms of these objects, rho t of x, and it's rather difficult. I'm not sure how far I succeeded in that. But for this particular example, let's then move on to how we can now talk about using that earlier idea of identifying transitions as communities in a recurrence network, using that idea and applying it to time series uncertainties. For that, first of what we do is we try to estimate probability of recurrence matrix, here denoted as this object A hat. So what I show here in this picture is on the top panel a sequence of probability density functions that we talked about before. So essentially how you read this top panel is that it is a time series, but each vertical line on this time series, so each vertical line on this time series essentially is a probability density function, the intensity of which is shown in this color map. So you can sort of say that, okay, what was the likelihood of the signal at 500, at t is equal to 500, and then you basically go to t equals to 500 and scan this matrix vertically, and you will find that, okay, the most likely values were somewhere just a little bit below 0. Now, this is again the synthetic example that I'm talking about. We'll get into it more detail in the next slide, but in this synthetic example, what I have done is I have artificially encoded 3 transitions. So the first transition is at this time point 1, where the dynamic sort of shifts to a different mean. The second transition is basically an extended transition at this time point 2, where the dynamic shifts back from this state to the other state, but according to a linear trend and does not do it abruptly. The third transition is something which is more interesting, where essentially the dynamics splits up from being a unimodal observed dynamics to a kind of a bimodal observed dynamics. And in each of these cases, what we now want to do is that we want to identify the transitions back. But for that, the first step is to estimate this probability of recurrence matrix. And I won't go into the details now. So long story short, what one can do is one can not precisely estimate the exact probabilities of recurrence because you don't know the exact covariance structures between any pair of densities in these sequence of densities. If you knew that, you could measure the probability of recurrence matrix precisely. In the absence of that, what we do is we come up with an estimator A hat for this probability of recurrence based on some upper and lower bounds that can be derived based on some considerations of using essentially Fresher's bounds and Fresher's theorems. Okay, so already you can see here that you observe these block structures that can help us detect transitions. But how do we go about it precisely? What we will do is we will use these use the estimated adjacency matrix A hat, and we will compute what's something similar to modularity, but not precisely. So it's the quantity that modularity also uses, but in a different way. So we'll compute the within community link fraction, which essentially means that if you have a given adjacency matrix, you just divide the matrix into two halves precisely at the midpoint of this adjacency matrix. Remember that we are talking about recurrence network, so this is different from other complex networks in the sense that the nodes of the network are the time points of measurements, and they have a precise ordering. So we can think of a midpoint in this array of nodes, and we can divide it into two halves, and we essentially then count the number of links that we have within the two halves and estimate what's the fraction of that as opposed to the whole link density. If high values of this within community link fraction would essentially mean that you have a more dominant block structures, and low values would mean that you don't. But what does high and low mean? So this is where I sort of deviate from the Bayesian aspect that Thomas mentioned. Although till now the discussion was more or less from a Bayesian perspective, but in order to really identify transitions in a binary sense, we again go back to the standard approach of statistical testing using p-values. What we would do now is that we estimate the within community link fraction for the observed matrix, but then we would randomize the whole degree structure of the matrix to create an ensemble of randomized versions of our network. And for each of those, we would get a new value of the within community link fraction, thereby estimating a null distribution of within community link fractions, and then obtain the p-values of, so basically the likelihood of observing an as extreme value of the observed link fraction as with respect to the null model of randomized degrees in your network. So how does this work in practice for this synthetic example here? I show this again once more, and I also compare it with sort of typical time series analysis on the right column here. So the top right panel, panel D, is essentially the mean time series when you take the mean value of each of these probability distribution functions in the top left on panel A. And here you can already see that because this bimodality is obviously not captured by the mean or the median, you don't even see it in the time series, and that's obviously not again going to go show up in the standard typical recurrence matrix that's shown here in the right column in the middle. Coming back to identifying transitions using within community link fraction, how we actually put it in practice is that we take a small window, and here's shown in this white square here, and we move this window along the diagonal of this adjacency matrix, and for each location of the window, we estimate the within community link fraction of that window. We randomize the degree structure of the tiny subgraph represented by the section of the adjacency in that window. We randomize the degree structures, obtain the null distribution, and obtain a p-value for the observed link fraction corresponding to the distribution there. And then we move the window to the next location, and then we repeat the process all over again, leading us to come up with an entire time series of p-values, which is shown here in the bottom panel. So, and then it's shown in a kind of on a log scale, and you see here p-values essentially for most of the time being very close to 1, but then at around the time points of these transitions, these time points 1, 2, 3, these p-values dip, telling us that the likelihood of the observed link fraction is very unlikely to have been caused by the randomized null distribution, essentially indicating that it's quite likely that we observe non-random transitions at these time points. Comparing it to the typical time series analysis framework, although you do have some kind of block structure in the first half, but it still does not really capture the transitions. It does not have high specificity, let's say, in that sense. So this was a kind of a contrived example, but the point was to motivate how this approach of identifying transitions using this notion of link fraction of recurrence networks communities could help us detect transitions, right? How do we apply it to a real example? Now I will talk about the paleoclimate data set from Northeast India, and essentially representing the Indian summer monsoon. Again, this is again a large part of my PhD was sort of to try to figure out how do we take the paleoclimate measurements and come up with a PDF sequence like this, but we managed to do it in the end. And what we see here is the paleoclimate proxy, which is a proxy for rainfall, this oxygen isotope delta 18O, and it goes from 30,000 years here at the top to the past, deeper into the past, to 44,000 years from before. Essentially, this proxy can be interpreted as when it becomes more negative, which is on the right, so the axes are a bit reversed. This is how geoscientists typically show this. So when it's extremely negative, going towards the right, that means you have a very strong monsoon. And when it's less negative, so going towards the left, you have a weaker monsoon. So obviously you see then these kind of sudden shifts and a kind of oscillatory pattern in the data. And we want to then identify not only these really large shifts, but we also want to be able to identify some of these smaller transitions as well. So as a first step, what we do is we take this probability density sequence and we estimate the probability of recurrence matrix, which is shown here on the right. And we move a very tiny window, which you can see also here in a small white square, to detect transitions using the method that I talked about already. So, and this small window is really a tiny window of 30 years, and we can do the statistical test for non-random block structures and get the p-values. That's now these are the final results, and I'm very quickly coming to the end of the talk. I show here the data and the results in the same plot. So let me just quickly talk about what's shown here. What you see in blue, the shaded area in blue is essentially the data, but now I do not show it in the color map view, but rather what I do is I just shade the area between the 5th and the 95th percentiles of the distributions at every time point. So essentially what you see here in blue is the part of the proxy signal which covers 90% of the probability mass at each time point. And in the green shading, you see the p-values from the block structure detection routine. And dips in the p-values are then the transitions, which we show by these plus signs, which are essentially the detected transitions. And then the green squares and the red crosses are essentially are transitions reported already in the literature from Greenland. So green in the Greenland ice sheet. And you do see that we do have correspondence between plus signs and the red crosses. So the transitions in the Indian monsoon do reflect what's known as these Danskard-Oeschger events in Greenland. However, these Greenland cooling events and green squares do not or always correspond to the detected transitions. So why is that? Still open question, and we are looking into it. To briefly summarize, what I tried to talk about today was that we can use communities in recurrence networks as indicators of abrupt transitions. Try to present a framework how we can show time series as a series of probability density functions. For me, what's really exciting about this is that this is a really from start to end and a comprehensive uncertainty-aware framework to analyze time series, and we show how we can use it to look at transitions in the Indian summer monsoon, paleoclimate data, and how they are, some of it, a subset of the transition, detected transitions are linked to Greenland events. That's more or less it. If I just have 2 minutes, what I just want to show again very quickly is that, remember I said that the idea of detecting transitions using recurrence networks is independent of uncertainties. So here is an example where you don't have uncertainties in the data. And what I essentially did is that I took the two time series for El Nino and Pacific decadal oscillation. These are essentially indicators of the climate in the Pacific Ocean. And you see the time series here, and what's color coded is essentially two communities identified in the recurrence network of these time series. So I took the time series, I did time series embedding here as well, and then I had a recurrence network existing in, I don't remember right now, but a three-dimensional, I think, phase space, and I look for communities in that phase space, and this is what I get back. And for me, this is really cool because the method itself does not really know about El Nino phases or La Nina phases, like extremely warm or cold phases, but it essentially classifies the data very neatly into warm and cold phases. I think that was really cool. Yeah, and that's all. These are the two papers that contain the material that I've talked about. And that's my group here in Tübingen, Machine Learning and Climate Science, and you can find us here on Twitter, and we're also on GitHub. If you have any questions, you can always write to me, email, or on Twitter. Yeah, that's it. Thank you for your attention.
Thank you very much, Bedartha. Do we have questions?
I have one if nobody from your...
Dimitri, go for it, please.
Yes. So thanks for the talk. It was very concise and understandable, at least from my part. I want to ask you to give us more details about how you estimate the probability distributions per time from the signal, and also how you estimate the recurrence map afterwards, this A hat that you mentioned. Yeah. So if you can give us a brief introduction to this, because I'm not aware how you did it.
Mm-hmm. Yeah. Okay. So the first question is actually easier to answer: how to get the probability density functions from the data. The answer is that there is no one way. So in this study, what we did is that we took that as a given, because that can really come about on how you actually measured the data. So in this paper, the first paper that we see on the slide right now, we basically take 3 examples. One is from paleoclimate, where it's really a slightly complicated way of combining different sets of measurements and coming up with this sequence of probability density functions. A second example actually is from this El Nino as well, where what we did is that typically what people do is they take a spatial, so El Nino is measured by measuring the temperature over a geographical box on the equatorial Pacific Ocean, and you have several grid cells on this geographical box. I think around 500 or 250, I don't know, maybe 250. And so you have 250 temperature measurements at each time stamp. So basically, if it's a daily data, so you have 250 temperatures for every day. If it's monthly data, you have 250 temperatures for every month in this box in the equatorial Pacific. And what people typically do is people take the average of these 250 measurements at each time point to create the El Nino index. What we essentially said is that let's not take the average. This extended geographical space essentially incorporates, induces a kind of a variability, which we then interpret as a kind of inability to fix precisely the temperature of the box, then again further interpreted as uncertainty. And so we take these 250 measurements and we do a kernel density estimator, use a kernel density estimator to estimate the PDFs. So that's a second example, a completely different way. A third example that we took in this paper was from financial data. And there the idea was that we had daily data, so freely available data, nothing too fancy, from Yahoo Finance. And what's the uncertainty now in the financial data? So what we said is that we don't have access to the sub-daily fluctuations of the stock markets. So we take the daily minimum and the daily maximum reported in the Yahoo data set. And we say that, okay, this is the daily minimum and maximum that has been reported. And that obviously the stock value did not go outside of these bounds. So given that we don't have any other information about the variations of the stock market within a day, we just assumed a uniform distribution between these two bounds and work with that as our sequence of distributions. So what I want to say is that how you get your sequence of PDFs is different depending on the situations. Okay, that was a very long answer, but nevertheless easier. The second question, how do we get the matrix, the estimator A hat? For that, essentially what we do is we don't have the covariance between two of our PDFs in our sequence, but we need now to estimate the likelihood of, so let's say we have the PDF at time 1, so row of x1, and we have PDF at time 2, row of x2, and we now want to find the probability of recurrence, and the essential quantity for that is the difference between the signal at x1 and x2. So you can create a new random variable z12, which is the difference of x1 and x2, x1 minus x2, and you can use Fresher's theorem to find bounds, hard bounds on these, on this new random variable z12. And using those hard bounds, you can essentially come up with bounds of the probability of recurrence as well. And that's sort of outlined in the appendix of this paper as well. I hope that answers your question to some extent.
Yeah, but if may I continue my question? Thomas?
Yes, of course, yeah.
But the recurrence matrix doesn't have the difference of the two random variables. It has the distance. And having two probability densities and taking the distance is not that easy to formulate. Even if I have an analytic form of the two probabilities. So I wonder how you do this, because what you explained now is about getting the difference.
Yes, and that, so the fundamental idea of a typical recurrence in the typical time series is essentially defined in the simplest case, Euclidean distance, right? And that's what we use in this paper as well. We are not talking about a distance between the distributions. That would be a very different kind of a recurrence. We still want to somehow have some continuity to the existing ideas of recurrence. So this is really, this A hat is not it's not incorporating distance between the distributions. No, it is really incorporating the probabilities of the difference between the signal at two time points. And that is how also a typical recurrence is defined. And we want us to somehow have some continuity with that notion. I hope that somehow clarifies it a little bit.
Well, at least Dimitri doesn't ask another question, so that.
No, please. I don't want to dominate. Thanks.
No.
I have, but I will not.
Question I saw in the chat is from Leo. Obviously, you now are at the machine learning and climate science group. And can you tell us something about how you are trying to translate these questions into, or these methods that you have, into a more machine learning framework? Or is machine learning, in that case, the typical way of saying statistical analysis?
Mm-hmm. Yes and no. I mean, I did not know about this, but at some point in the last years, I sort of was told that what we do is this kind of statistical analysis, is also a kind of machine learning. But anyway, I had no idea. But for me, what's interesting is that personally, what I find interesting also within this group and generally is to think about reduced representations of data. And the communities that we come up in recurrence networks, for example, in this example, right? I mean, this is a kind of a reduced representation of the data. I mean, not in this particular plot, but being able to classify your time series in terms of these two warm or cold states from these communities, that's a reduced representation. You essentially condense your entire dynamics into a kind of a bivariate signal, just has two values from now on, like, you know, warm, warm, cold, 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 warm, 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 cold, 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 and so on, right? I keep an eye out to somehow try and steer a little bit our group in trying and exploring more of these reduced representations. And also what interests me is how do different ways of coming up with reduced representations relate to each other, right? So one of the current projects that I am personally interested in and working on right now, and we're sort of writing a proposal for it, is how are a standard reduced representation of climate data, spatiotemporal global climate data is these empirical orthogonal functions. So you take SST data, sea surface temperature data from all over the globe, and then you do you estimate the EOFs, and then you find that, oh, okay, just the top 10 eigenvectors essentially describe more than 90% of my variance, and then I basically can describe almost fully describe the variability of my data with just the top 10 modes, right? That's a reduced representations. An alternative way of reducing the climate data set is to use climate networks, which Niklas and is an expert in. We've also done a lot of work, our group has done. So for me, then it's a really cool task to sort of ask and find out how are these two representations, these two reduced representations of the same climatic systems, how do they relate, right? So I'm interested and then one can think of like variational autoencoders, and I don't know what, you can have 10 different standard machine learning techniques also giving you reduced representations. And yeah, that's for me very interesting, amongst other things.
So obviously I have a question myself, and that is more philosophical question about how you actually decide these probability densities around your data point. Mm. You said that more or less the measured one gives you the mean of your probability distribution. Now, obviously, we don't have access to the true value, but one would assume that there is a true value, and around that true value there exists a probability density distribution, which is sampled, which gives you the observed value. Yeah. While one cannot actually do this with real data, I imagine that one could try to test the difference between what you are doing and this more philosophical concept on synthetic data. And have you tried this, and what kind of effects did you see, or what would you expect if you haven't done it?
Yeah, so what I typically do on synthetic data is I assume a true signal with some true mean and variance, and then I do a sample of that true mean and variance, and I I basically then sample my true signal several times and then approximate the mean and the variance. And then and most of the time, if I have, I don't know, like around 50 or 100 samples, you more or less get it right. So for example, if we go back to this synthetic example that I showed here, right? So in terms of detecting these transitions, which are, let's say, on a slightly bigger scale than the individual. So I'm guessing, so if I have 100 samples from a 100 samples to estimate the true mean and variance of a single distribution at a given time point here, it would not be so off as to give me a wrong answer in detecting transitions. So that also matters somehow. What is your end goal? I'm sure there might be other questions, such as trying to estimate the power spectrum of the signal based on your sampling, where this might really play a role. I haven't got to that yet, though.
I mean, I completely agree. When you are doing it with synthetic data, that problem can be avoided by doing multiple samples. But since we both worked with paleoclimate data, where we know we are lucky if we get something like a couple of 100 points in the time series.
Yeah, exactly.
We certainly don't have the sampling unless Sebastian comes with a really, really good time series. Yeah. Where we can do this kind of estimating the distribution based on many points. Yeah. And so I think it would be an interesting thing to do it with one sampling, something like a realistic noise source on it. But maybe I'm taking up too much of the time. I've seen Lyle, your hand was up.
Yes. I was thinking, if I may ask a question. Thank you, Bedartha, first for a lovely talk. I was wondering about, there was this question earlier, you know, as you say, you are not taking the distance between probability distributions. That's not your statistic. But I'm wondering a little bit if that might still not be rather a good idea. For example, there are these known methods of computing distances between probability distributions. Yeah. These things are based on using Fisher information. There's some work of Amari and his collaborators. It goes back quite a long time. There are these rather interesting ways of defining distances between probability distributions. For example, if you have, I think the distributions you're looking at are more general than, say, normal distributions. You'd want something more than that. Mm-hmm. But if it were just the normal distributions, it's well known that the correct way to measure the distances between these is to essentially these distributions, they are points in the Poincare upper half plane, and the distances can be computed very easily. Mm-hmm. Now, for more complicated distributions like the bimodal ones that pop up, multimodal ones that you have, it would be more complicated, but I think still maybe rather interesting to see if there was a sudden change in distance. I mean, is that something you've considered?
Yeah, that's a good point. We did consider this at some point, but to be honest, we did not end up working on it. It would definitely show interesting things. Yeah. One would have to, so when we were talking about it, me, Niklas, and Alyosha, so essentially what we came to was that one would have to be careful about how you interpret. So thinking in terms of climate data. So maybe you can construct, let's say, the distribution of temperature. So let's say you have daily temperature data, and now you sort of aggregate it to a yearly distribution. So you transform your daily data to get a distribution of temperatures for every year. So now you have a yearly time series of probability distributions of the temperature. And now, if you were to then use some kind of metric that can give you the distribution, the distance between two distributions, you can talk about when did two distributions when were two years close to each other, in the sense that the distribution of temperatures were close in these 2 years. So that would, of course, give us other interesting insights into the data and its variability.
Yes.
Definitely a good question.
It's just a different approach. I thought that since you have this very nice approach of probability distributions, treating it like that, then maybe the distance between probability distributions might be a reasonable thing to do. So,
yeah, for sure. If somebody is going to work on it, I would be happy to see it that work someday.
Just a thought.
I just did not have the time to do it.
Thank you.
Okay, so I really hate to do this, but given that some of us have to go to another meeting at 5, I think I'm going to close the discussion. Thank you, Bedartha. It was a real pleasure to have you and to hear something new about paleoclimate analysis.
Thank you.
And yeah, I hope I see you soon in Germany, or you come over to us. I mean, that's also always an option. Yeah.
Cool.
Okay.
Okay then. Bye.
Bye.